Hello and welcome to a calculus tutorial by Physics Man Education. I'm Physics Man, and today we're going to be talking about some general properties of polynomials. So what do we mean by a polynomial? A polynomial is the summation of a series of terms that can all be described by a similar format. You have some coefficient times x to some power. And we'll denote the coefficients by a subscript. So the kth term of our polynomial will be x to the power of k times the kth coefficient. What does that look like? Well, if we write y as a function of x being some polynomial, it's going to equal to a0, x to the power 0. This term is actually quite important. X to the power 0 is just 1, so this term is really just the constant a0. Our second term will be a1 times x to the power 1, a2 times x to the power 2, plus yada yada yada. I think you get the point. In general, there may be n terms. So we can say a n x to the power n and every integer in between. What we want to do first is we want to condense this and express it as a sum. We use the symbol sigma, capital sigma. It's a Greek letter that looks like a fancy E, to mean a sum of terms. And we're going to write the general format of each term. But we need to also in some way express what each term will be, what makes it unique, and how many terms there will be. So we say that our first term will be when k equals 0. That's our first term. And our last term will be when k is equal to n. So this means that there will be n, I guess, plus 1, because we're starting with k equals 0, terms, where each term will be k equals 0, plus k equals 1, plus k equals 2, etc., 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 up until k equals n, just like we have written there. In other words, this is just a more condensed way of writing that. Not really all that special. And to make it a polynomial function, we could write that y as a function of x is equal to that. Can we think of any examples of polynomials? Sure, we've studied a couple already. The first one would be a linear polynomial. A linear polynomial is a polynomial that describes a straight line. That's why it's called linear. Now, when we were talking about linear functions or straight line functions, we learned it in this general format. Y as a function of x is equal to ax plus b. Does this look very different than this? Well, sure. The main difference is that all of these terms where k is greater than 1 don't exist here. Our k equals 0 term does exist, because if we multiply b by x to the power 0, well, x to the power 0 is just 1, 1 times b is just b. So really this term exists, and this term exists, and the rest are all gone. So we can write it like this. Now, by comparing like coefficients, remember that x is just x to the power 1. By comparing like coefficients here, we can see that x to the power 1, we can extract a is equal to a1, and we can extract that b is equal to a0. And that's what we really mean when we write down this expression. When I taught this expression to you, this is really what I meant, was that this straight line can be described by a polynomial where n, our maximum number value for k, is equal to 1. This number n, by the way, denotes also the order of the polynomial, which is a term that we'll want to get familiar with in a few minutes. Let's talk about some properties of this straight line. We can ask first, how many inflection points does this line have? An inflection point is a point where the slope changes signs from either positive to negative or from negative to positive. The slope of a straight line is constant, so it never changes signs. If it starts out positive, it'll be positive the whole way, or if I drew this with the opposite slope, it would start out negative and be negative the whole way. So the maximum number of inflection points is 0. What about the maximum number of roots? Well, this linear function, as x goes to negative infinity, the one that I drew, y would go to negative infinity, and as x goes to positive infinity, y would go to positive infinity. Now, if I drew the slope the other way, the opposite would be true. X negative infinity would mean y positive infinity, and x positive infinity would mean y negative infinity. But for this one that I drew, it goes from negative infinity to positive infinity. It can only do that if it crosses the x-axis at least once. But because there's no inflection points, meaning that the slope doesn't change sign, it can only have one. So the maximum number of roots is 1. Can we think of any other examples of polynomials? Sure, we just studied quadratic functions. So, our quadratic function might look like this. Right? And we learned the expression y expressed as a function of x is equal to ax squared plus bx plus c. Does this look like a polynomial? Well, sure, it does. It looks like a polynomial where the terms greater than x squared don't exist. So in other words, it looks like a polynomial where n is equal to 2. So we can write it like a polynomial. We could say a naught times x to the power 0 plus a1 times x to the power 1 plus a2 times x to the power 2. And we could do the same thing where we compare like powers to extract what these coefficients relate to in terms of a, b, and c. At this point you may realize it's kind of pointless to do so. You could just calculate these coefficients for face value. What I would like to know is, what is the maximum number of inflection points of this parabola? Well, parabolas all have exactly one inflection point that occurs at their vertex here. So IMAX, aside from being a place where you can watch movies, for a quadratic function is equal to 1. What about the number of roots? Well, this parabola that I've drawn doesn't cross the x-axis or touch the x-axis, so it has 0 roots. It can have 1 root, it can have 2 roots. So r is equal to 0, 1, 2, all the way up to r max. And what is the maximum number of roots for a quadratic function? R max is equal to 2. Great. There's one more step I want to go on here before I start talking about the powers and the orders of the polynomial in more detail. I want to know if I can express this function in that format. And I kind of hinted at it earlier when I mentioned that this quadratic formula looks exactly like this, where n equals 2. So yeah, I can express these in that format. All I have to do is here, the maximum power of x is 1, so I have to substitute n equals 1 here. Great. And I could do the same thing here. Now, there are two things that are very important here. First of all, it's important to notice that this power becomes the new n value. This highest power becomes the new n value. The other thing that's very important to notice is that I have to start with k equals 0. If I make the mistake of starting with k equals 1, this constant term, or in other words, the c coefficient here, or if I do the same here, this constant term, or the b coefficient, don't exist, and we don't have the general form of these functions. So you have to start with k equals 0 for this to work properly. Now let's start talking about the order of a polynomial. The order of a polynomial is simply given by its maximum exponent. So the order of the polynomial is simply equal to n. Keep in mind that's not 0, that's a capital O for order. The order of the polynomial is equal to n, the maximum exponent of the function. And based on what we've done here, we may start to see that there's a relationship between the order of a polynomial and certain properties of the function, like its maximum number of inflection points. Just so. The maximum number of inflection points of a polynomial is the order of the polynomial n minus 1. In fact, we could go a step further. Because a linear function has to go from one extreme to the opposite extreme as you traverse positively through x, the number of inflection points has to be even. So, we could say for, I'm going to write this down here. For an odd function, the number of inflection points will be equal to 0, 2, 4, etc. up until I max. Keeping in mind that I max is going to equal to n minus 1. For an even function, we require the opposite to be true. Because for this parabola, for example, we go from positive infinity on one extreme x to positive infinity on the other extreme x, which means that the number of inflection points has to be odd. So, we could write that I is equal to 1, 3, 5, etc. up until I max, where the maximum number of inflection points is still defined by n minus 1. What about the roots? Well, the maximum number of roots is given by the order of the polynomial. So a polynomial of order 100 could have potentially 100 roots. So that's just equal to n. But what about the actual roots? Well, for a linear function, there has to be at least one root. Or for an odd function in general, because of the behavior where it can start at one extreme in y as you go to one extreme in x, and go to the opposite extreme in y as you go to the opposite extreme in x. So there has to be at least one root. It has to cross that x-axis at least once. But then it could be any integer value thereafter. So it could be 1, 2, 3, etc. up until our maximum. What about even functions? Even functions, we find something quite similar, except that an even function never actually has to cross the x-axis. So our even roots actually start at 0 and then follow every integer thereafter, up until the maximum number of roots. Keeping in mind that the maximum number of roots is just n. And there you have it. there's everything you're going to need to know about polynomials for now. We will discuss them in more generality later. In fact, we're going to do some pretty fancy things with polynomials, but that's going to be in the future. So, this has been produced by Physics Man Education. I'm Physics Man, and I'll see you in that future where we do fancy things with these.